All right, it is 12 o'clock. We're going to get started with our February webinar. Thank you all for attending, and thank you to everyone who is joining on. Welcome to the Transportation Infrastructure Durability Center's February webinar on guidelines for the modeling, design, and construction of integral abutment bridges. My name is Aaron Schanck, Communications Specialist for the TIDC, and I will be moderating today's webinar. The Transportation Infrastructure Durability Center is the 2018 US DOT Region 1 University Transportation Center located at the University of Maine's Advanced Structures and Composites Center. TIDC's focus is on extending the life and improving the durability of transportation assets through 4 research thrusts: advanced structural and performance assessment, development and implementation of novel materials, advanced structural systems and applications, and enhanced performance through innovations in safety, resilience, and connectivity. TIDC has 6 member universities within the New England region: the University of Maine, University of Connecticut, University of Vermont, University of Massachusetts at Lowell, Western New England University, and the University of Rhode Island, in partnership with the 6 New England DOTs. Today's webinar will consist of a 30-minute presentation followed by a Q&A session. During the presentation, please use Zoom's Q&A feature for any questions you have for our presenter, and we will go down the list during the Q&A session. If we don't get through them all during the scheduled time, there will be a link at the end of the webinar to submit any further questions, and we'll be sure to send you a follow-up email. Our presenter today is Dr. Susan Faraji. Susan Faraji is a professor of structural engineering in the Department of Civil and Environmental Engineering at the University of Massachusetts Lowell. She has 4 decades of teaching, research, publication, and consulting experience in the field. Over the past 40 years, she has taught a wide range of courses at the University of Massachusetts Lowell, from basic mechanics to advanced design and analysis courses. She also has extensive industrial experience, having worked with a variety of government agencies such as the US DOT, US Army Corps of Engineers, the Massachusetts DOT, Rhode Island DOT, VTrans, and the NCHRP, and a variety of consulting firms such as the Shaw Group, McGuire Group, Purcell Associates, Bayside Engineering, YAS Ventures, and HNTB Corp. Following the presentation, Dr. Faraji will be joined by James LaCroix of the Vermont Agency of Transportation. Jim is a Vermont Agency of Transportation state bridge engineer and project manager. He has worked with VTrans for over 24 years. He is a valued collaborator for the TIDC, serving as technical champion for the IAB Guidelines project that is being presented today. Jim holds a bachelor's degree in civil engineering from Clarkson University. And so with all of that, Susan, you are free to share your screen. Are you having any troubles, Susan?
Professor is saying that you have not allowed her to share.
Thank you. Now I can. Thank you, Aaron. Hello, everyone. Thank you for attending today's presentation. So it has been a long journey with TIDC project. The project started originally under the title that you see, and it has gone the different direction based on the input that I have been getting from different companies and TIDs, different Department of Transportations. And do you see my screen?
Not quite yet, Susan.
Oh. You see it now?
Yep, we see it now.
Perfect. So let me just start. All right. So as I said, it just like it has been a long journey. The original idea was this particular research was about input from other people, how to improve quality of design, analysis, and construction of integral abutment bridges. So what I have been doing is I have been looking at different aspects. Actually, let me show you the last thing that is listed on this slide, which was parameters controlling the in-plane rotation of skewed integral abutment bridges under thermal loading. And this was analytical work that I did and has been very useful in a sense of that the issue we have with integral abutment bridges, especially when it is skewed, is a problem. So this is a presentation. I'm going to have a presentation on this topic in France this coming July. And so I have presented that particular topic many times. I have few slides that I can go over those. The other one is the middle of the page that was looking, I was looking at impact of abutment wall height, span length, and soil profile on design of piles and girders. But today, my most focus would be the first topic here, which is the impact of use of EPS or geofoam as a backfill material in integral abutment bridges, and looking at that, how that impacts the girder and pile design. But major issue with that is how do we go about to make sure that we do that correctly. So for this particular TIDC project, from the beginning, I have created many sample three-dimensional finite element models, and with different span lengths. And so it just like to look at different abutment wall height and soil condition and all that to use for analysis purposes. The type of soil that I have been using behind abutment walls and around the piles was original information that I had for one of the bridges in Massachusetts. I have worked in the past to make sure everything is consistent. So now let's look at this particular topic, that use of EPS. When it comes to use of EPS for reducing pressure behind the abutment walls, one of the issues that we have is how to model, how to consider our EPS and make sure that the EPS is giving, or should we use linear springs? Should we use non-linear? How to go about? And as you see here, it's just like when you have a abutment wall and we use EPS with different thicknesses, it depends on our span length and also abutment wall height and all those. We decide what kind of thickness do we use for those EPS. And then we go through our analysis, and the soil, compacted soil under approach slab is behind it and all that. I spent quite time on that because I got input from people that it is very hard to see what we are doing. We are knowing that use of EPS would reduce pressure behind the abutment wall, which is a good thing. But the question is it working properly, or what we are modeling is correct or not? So I look at linear springs and all that. Finally, and it was very difficult from manufacturers to get information about EPS. So finally, I decided to go into the approach of taking my EPS and model it as a block, as a solid block. The same way that we model that are like pile caps as a hammerhead or as a solid, and I treat it the same way. This way, I didn't have to second guess that, am I doing it right or wrong? And so this is what I did. And the other issue that I was dealing with was the matter of usually we have our modeling technique. So I'm talking about two things here: the modeling technique that impacts our results. The other issue we have is just when we have our girders. In my sample bridges, I had 7 girders. And how do you link them together? So original design that I had from a 150 feet bridge in Massachusetts, I had the cross bracing that I was using, or the cross bracing sometimes should be, it could be in a form that I'm showing you on this slide here. So makes modeling very difficult in a sense of we have to, how do we connect it? How do we define additional nodes? Sometimes these cross beams are coming connected between from the web to the flange. And sometimes people model it like different papers. They model the flange separately, the flanges separately, and the web to be able to do those cross bracing. So what decided to do, I said, let me reuse, because, one other problem we have with three-dimensional model, the way we model our slab and girders, we are linking them together. It is too flexible compared to actual bridge, which is slab and the girders work like a grid together. So I said, what about if I define, rather than using like cross bracing like that between girders, use solid plain element? Of course, this is the option was available to me on the GT Studio software that I'm using. And this on the picture on the left is showing you how that is, because first of all, this there is a master node that takes that at not mid span. It just like the width of the bridge at the middle of it, and links those different nodes that exist on the girder to that node. In other words, it creates a rigid system. Of course, this was tested is that the results are pretty good compared to what we have if we really go through what we have been doing. So again, as I said, two different important factors here. And this is a topic, as I said, I'm going to be presenting in March in University of Miami on symposium. And so again, I repeat, the two aspects is how do we define our cross bracing, and the other one is how accurate is our modeling on GeoBlock. So now let me show you a few slides on the results for comparing using EPS with different thicknesses with compared to the dense soil. If you notice in all of these, I just, you have to say, well, you talked about 7 girders. So the difficulty with integral abutment bridges that we call it edge effect, when you go towards the edges of the bridge, the impact would be different. All the girders are not going to behave the same way. And especially it's more critical on the piles. So in this particular examples I use had 7 girders. So we look at the plate girder at the center line. and the center line of the bridge, make sure those impacts are not there. So this plot here shows the axial force, the one to the left, and the plot on the right shows that moment profile, axial force, and changes from the abutment to abutment. So this is for 550 feet span bridge, and with the abutment wall of height of 12 feet. So what I did, as I said, you saw that I had different examples running from 150 to 550 to see the changes that we are going to notice based on span. And so this is for the longer span, three-span bridge. So now you look at this table, it just like take some of this information on those plots and listed in this table that just shows that how much changes do we see in axial force at the abutment, because the bottom line is the connection. The more important factor in girder design is we look at the connection, especially if it's the moment connection, like my example, with the wall. That, as you see, by using EPS, that we giving more flexibility, and then we just, the axial force in the girder decreases, and so is the bending moment. So then we look at the pattern. So then the question rises, if the wall is moving more, it means would not have a good impact on the piles, because the piles have to move more. So in this slide, you see that on the left shows the displacement profile for the pile, and on the right, it shows the bending moment profile for the wall for the same 550 feet long span. And just make a comparison between EPS and dense soil, and it is obvious there is increase. So it's summarized in this table here that delta, the first row, shows displacement at the deck level, and the second row here shows displacement at the pile level, which is at the bottom of the wall. And then M1 shows that the moment at the connection between the pile and the abutment wall. Of course, all these examples for 150, I had a range from 150 to 550. For shorter span, I'm using HP, and for longer span like this one, I'm using W shapes for the piles. So as you see here, that by using that EPS, there is some increase in bending moment in the piles. And this slide here shows the wall movement that the plot on the left shows the abutment to the left and abutment to the right. The movement, all of the slide that you see is under thermal expansion of 100 degrees. And we have done lots of analysis for truckload, for dead load. Of course, we know that the temperature load does not happen by itself, is accompanied by dead, but what the focus here was just the impact of temperature. But I have tons of results that for dead plus temperature, for the truck, that for TIDC project, that I have a complete documentation that I have to submit at the end of this coming summer. And those who are interested, they can have always access to it. All right. And this is, again, shows the wall movement for shortest span that I have used for my sample bridge. And as you see here, the impact is very small. So the same thing for 550 here, you see that I have the plots of axial force and bending moment over the tree span of the for the girders. And in this case, for 150 feet bridge, the height of the wall was 8 feet. Again, you see the similar pattern, but this time when we look at the maximum, the bending moment in the, when we see the value in the bending moment, again, we see that decrease, which is in EPS compared to the dense soil behind the abutment wall. And actually, you see major changes. But then here another displacement profile for the 150 for the piles that shows the same similar pattern. And this is the table that, again, we just comparing like bending moment M1 at the connection between the pile and abutment wall. You notice that for the case of the 550, there was a huge increase, but still is a large increase, but because the moments are small, the impact is less noticeable on the piles. And in this plot here, when I was just trying to look at the what I call it grid system, introducing those rigid plane into my model, and as you see, the other plots of axial force and bending moment was smooth, but when you use this rigid plane elements, you just see where the bumpy location is just where those plates are coming in, but still the results are very similar. Try to working on it to say how we make those points more smooth. The reason I'm insisting on it, it just makes modeling so much easier compared to trying to introduce cross bracing. All right, so the bottom line is it is obvious that use of EPS is a major impact on our girder design and our piles and design of our abutment walls. But it is obvious that EPS would be more critical to be used when we have much longer spans. Very quickly, I want to go through, because time is limited, I want to go over, I have presented this particular topic, looking at impact of grade profile and span length and all that in the previous presentations. And one of the things that it is important based on what I did here, you see when I call it K1 and K2, it's just matter of because interval abutment bridges or relative stiffness matters. What is important here is it really doesn't matter. The difference of the stiffness is coming just from sloping ground, comes from the abutment wall height differences, or compactness of the soil behind one abutment respect to the other. So that's why it just like it is important. One of the things my finding on this was, when you don't have perfect symmetry at your abutments, you really need 3D model if you want accurate results. So very quickly, this is all of these plots that you see. Mr. Harsh Gandhi, which is my PhD doctoral student, has been creating it, that I'm sharing it with you. So for example, here, you see that I'm showing that for 150 feet span bridge, when we look at one abutment compared to the other abutment is have the same identical conditions, or one has 5% more stiffness compared to the other. And so it just shows that what happens to the change, what we see over the abutment wall height. What is the impact of abutment wall height and compared to when the stiffness behind the walls are not the same? So these are all going to be in my report, and I have created lots of plots that for preliminary design engineers can use to help their design. So I'm going to go quickly through these. And so this would tell you that what I'm trying to say is when you don't have symmetry at your abutments, so it is crucial that you have if you want you design your piles more accurately, you have to go really with 3D, because it just the impact cannot be neglected. And also, this is a topic that parameters controlling in-plane rotation of skewed integral abutment bridges. This analytical study, I think it was very crucial, and it has many benefits because I'm going to again present this in Europe this summer in a conference and would be published. And based on this parametric study, it is obvious that what controls in-plane rotation of the bridge is not only skew angle, and the rotation of the deck of the bridge depends on length over width. A over B is the ratio of length over width of the bridge. So if I have this two bridges the same length with different width, they are going to behave differently. So again, I have plots, equations that very easily can be used. And the other thing is tangential stiffness coefficient on the boundaries of the bridge. What does that say is, let's say, for example, that I call it beta factor, that comes from the friction between the wall and what is behind the wall, and also impact of the wing walls. Let's say if your wing walls are lined up, the resistance would be less compared to the wing wall coming at some angle, all right? The other important factor that is just again, I would make it available if it's not, boundary conditions are not symmetrical. So whatever I was talking about for non-skew bridge, I'm talking the same thing here for skew bridges, that if boundaries conditions on one side, one abutment compared to other are not the same, all would be controlling the results. So here what you see is just showing you that displacement at different corners of the bridge when you have the ratio of length to width of the bridge 1. So the picture on the left shows that displacement at obtuse corner, and the one on the right changes the displacement at the acute corner. You see what happens to acute corner? Let me go to previous slide. You see here obtuse corners and acute corners. So at obtuse corner, so if you look at many design, they say under 20 degrees, as you notice, is not just this plot shows really, this analytical work shows that really around 20 degrees, that's the way that displacement at obtuse corner reaches its maximum. But then if I look at goes to a maximum, and after that decreases. If we go to acute corner, is consistently increases. Consistently, actually what I'm saying is this shows based on, when I say decreases, is because I'm comparing it for beta. What is the beta? Beta is the friction force behind the abutment wall. all right? The normal one for our practice is around 5%. So I'm just comparing 0.01% up to 15%, which is not, I don't think we never hit that. And around 0.05 is logical value. So here again, we go into the case that length over width becomes 3. So now you see what happens at obtuse corner? The displacement goes negative. I mean, when I just say when I say it goes negative, in a sense of we look at the case of when we have no resistance. All right. So it means it just goes below 0. And then the same thing for the same pattern that you see for both sides. This slide here shows skew angle and versus rotation versus skew angle when K and the boundaries are not the same. So in other words, more variation, how that impacts the behavior. And again, for one of the things I said that usually the maximum rotation reaches its maximum at 20 degrees, but as you see here, it just changes based on different case and different value of beta and span. I'm going to skip these. And now what I'm showing here is for the A over B of 3. And we did that. And what the point is here is one of the things we experience for skew integral abutment bridges is when, based on different conditions, the acute coordinate might go in opposite direction and cause cracking and all that when unexpected. So again, I find that this is very useful. I have tested this on a sample bridge and is consistent with what I'm showing you here. Now, because of all these work that was done on TIDC project, now we were lucky to get a subcontractor to a bridge in Hartford, Vermont, and we are funded. UMass is funded by HNTP Corporation, and so I have a team that we are working all together on this new project. The amazing thing about this project is the many things that we have learned from TIDC project we are going to implement. And one of the reasons, like for example, in TIDC, when I was using 550 feet span, because this particular bridge was 550, and I was just looking for proper numbers that made sense. So that's why it just like one of my bridges has a span of 550. So in this particular project, we have been, right now, the construction phase is coming to end. And then what we are going to do is we are going to just do the data analysis and data collection and data analysis. Now I'm going to ask Mr. Harsh Gandhi, the PhD student that has been working with me on TIDC project, and also working, now he's working on this project to talk about instrumentation of the bridge. Harsh, do you want to start? You are muted.
Can you see my screen? All right.
Okay.
On the next.
Let me stop. Okay, go ahead. Go ahead.
My screen is visible, right?
Yep, go ahead.
All right. Hello, everyone. So my name is Gandhi, and I'm a PhD student. So today, on my part, I am going to talk about the description and the installation process that we took at the New Hartford Bridge number 7 in Vermont. So on my screen, on the left side, as you can see, the map image of the old bridge, which is situated on the White River Junction, which was replaced with this new integral abutment bridge with the span length of 550 feet. This bridge is kind of novel in sense of it has a skew angle, as you can see from this image, of almost 20 degrees. On my right, you can see the old bridge that was there, which got replaced with this new bridge. And in below, this picture is taken on the day of the bridge was open to the public. So on the corner, you can see the kind of old bridge which has been closed now. So this is the typical elevation section for the New Hartford Bridge number 7, which has the 3 span divided into span 1 and 3 into 160 feet and the mid span of 230 feet. The typical slope for this new bridge is approximately 3.8%. And in this image, we can see the typical cross section of the bridge from the side from the abutment 1, where we can clearly see that this bridge has 4 girders equally spaced at 10.5 feet, and it is equipped with the cross bracing as well. Now coming towards the abutment, so this is the elevation profile for the abutment 1 and abutment 2. In here on the left side, we can see that abutment 1 has the 4 girders and 10 piles installed at the abutment 1. Those piles were pre-drilled and put into the caisson with the equal spacing of almost 4.6 feet apart. And here on the abutment 2, we can see those 4 girders, but additional 1 tiny girder as well. So this is the splayed girder that has been installed just to support the sidewalk at the abutment 2. Similarly, at this abutment 2 as well, 10 piles have been installed at the 5.5 feet apart, and those piles were hammered down, not the pre-drill due to the site condition. This is the elevation view of the earthwork at the abutment 1, where we can see the girders coming up. This is the abutment wall. And here we can see that EPS 45, which is expanded polystyrene, also known as geoform, is being used as an backfill material. And behind that, there is a granulated compacted sand. So the whole backfill material is a combination of EPS 45 and the granulated dense compacted sand. Now, as I mentioned that the novelty of bridge due to its big span length of 550 feet, the skew angle and the EPS as an backfill. So to monitor the behavior of the superstructure and substructure accurately, there has been many sensors being installed, such as strain gauges, extensometer, tilt meter, pressure cells, barometer, and we are also working with the ground penetrating radar as well. So I will go with each sensor line by line. And to begin with the strain gauges, so there are like total number of 234 strain gauges been installed on the girders and the piles. So for the girders, the total numbers are 58. So 58 gauges were installed in combined with girder number 2 and girder number 3 in the configuration as shown here in this figure. So this is just the half span. The other half is just a mirror image of this configuration. And here at the abutment level, we have installed these strain gauges at the each end of the flanges and in the middle of the web, and on the remaining place, just the opposite end of the flange. And by doing so, we are going to analyze the axial force, the bending moment, the torsion, and the shear using the data that we will collect from the strain gauge. And each strain gauge installed here has the capacity to measure the change in strain up to 5,000 microstrain. So these are the pictures of strain gauges when they were getting installed on the girder. Here we can see that this is at the location 1 because one on the flange, another one on the flange, and one in the middle that we can see. And this is the other side of the girder. So those are the pictures of the strain gauges installed on the girder. Now we have also installed 176 strain gauges on the piles, and out of 10 piles, for the end effect, we have installed on pile number 1, 2, 9, 10. And in the middle, we have installed the gauges on pile number 5 and 6, where the top two location at each elevation, the strain gauges are configured in this configuration where the 4 gauges were installed on the flange, where the remaining location, we have just installed 2 gauges. And the reason for the 4 gauges on the top 2 location is due to the importance of stress and force exerted on the top level of the pile. So it is very important to notice all the change happening on the top location of the pile. Same thing, here's the picture of the gauges that were installed on the pile at abutment 1. Similar to the strain gauges, we have installed the total number of 16 extensometer on abutment 1 and 2 just to see the contraction and the expansion happen on the bridge during the temperature changing event. And for those, 4 extensometers were installed on the wall and 2 on the each side of the geoform on the wing wall. So just that we can clearly measure the amount of movement happening at the abutment level. And these extensometer are capable of measuring up to 6 inches of expansion and the contraction. So here's the image of those extensometer that's been installed. So this is the extensometer tube, the base plate, which is rested on the face of the geoform. And then later the backfill with the granulated soil was been here so that we can clearly measure the amount of abutment wall movement. Now, to measure the amount of pressure being gonna exert from abutment wall to the geoform, it is important to measure the pressure. And so to do so, we have installed like 26 pressure cells on the abutment 1 and 2, where 9 on the abutment 1 abutment wall and 2 on the each side of the wing wall. Same thing goes for here, the pictures when the pressure cells were installed on the abutment 2 wall. Now, the next sensor that we installed was the tilt meter, and tilt meter was important to notice the amount of rotation that gonna happen to the abutment level as well as the inclination that would happen to the abutment level. So total 12 tilt meters were installed at the abutment 1 and 2. And these are the pictures of those while they were getting installed. Now, as I mentioned that those were all the installed sensor that we did on the integral abutment bridge at abutment and on the girder level just to measure the bridge behavior. But we are also using the ground penetrating radar just to see the amount of movement that would happen at the geoform level and at the backfill level. And to do so, we have installed the steel plate as a reflector for the electromagnetic wave that been used by the GPR. And by using this configuration, we will measure the amount of displacement or the movement would happen at the geoform level and at the backfill level. So those are all those instrumentation that we're gonna use to measure the bridge behavior. And during the construction, we have taken so many pictures of bridge, and let's go through those pictures. So here, this one shows the pile that are going to be installed at abutment 1 and 2. As I mentioned earlier, that abutment 1, the piles were pre-drilled. So the pre-drilling were happening at the abutment 1 level. And this is the causeway building for the bridge construction. These are the pictures of the piles after getting installed at abutment 1 and at abutment 2, from pile 1 to 10 at abutment 1 and 11 to 20 at abutment 2. these are the casting of the pier. So pier 1 and pier 2 is going to be at this bridge. This image shows the EPS that we were talking about. So this is the abutment under construction, and then these EPS were installed adhesive and attached to this abutment wall, and later the backfill was been here. So this is EPS 45 that's been used in this project. This image shows the gutter installation at the abutment from the abutment 1 side. So gutter 1, 2, 3, 4 can be clearly seen, and the cross bracing that we were talking that is installed here. Now, these are the gutters during the installation and the few images of the gutters after getting installed from different abutment sides. So this is the, in here, left image that shows the backfilling of abutment 2. So the girder here in the black, which is covered, are already installed. And after the girder installation, as I mentioned, the granulated, compacted, dense backfill going to be filled in multiple layer. So here the backfill is getting compacted and getting installed in the multiple layer at the abutment 2. Few more images. And now this image shows the data logger system that has been installed. So all those sensors that installed needs to get data collected. And by using this data logger system, they are capable of collecting data at 20 Hertz frequency at any given time. Currently, which are used at 15-minute interval using. But by using this data logger, we are able to remotely collect all the data from all the sensors that I have mentioned earlier. This is UML team during the installation of those data logger, UML team during the different construction phases when the piers were getting casted and the piles were getting installed. And this image shows the completion of the bridge. So this is the new bridge that replaced the old one, and same the roadway profile of the new bridge. This image is taken during the live load testing of the bridge after it got opened. So HNTB, UML, and the VTrans people are together working on the day of the live load testing to complete the construction of the bridge. So that was all the detail from the 550 feet.
Okay. Thank you, Harsh. One thing I want to say, because I think we are running out of time here, we cannot, this is a HNTB project. We are in charge of data collecting and data analysis. And we have made many site visits, and that's all those pictures you saw. There were a bunch of questions. Can I answer it? Because I saw on the question section. Is there time for that?
Yep, we're gonna jump into Q&A right now, Susan. I'll field these questions to you and to Jim. The first one, I'd like to give Jim LaCroix a couple seconds. Can you talk about your experience working with UML on this project, both in the analysis and in the bridge number 7? Is there anything you'd like to say on that?
I'd just like to say that Vermont's pretty excited about this project. This is about 150 feet longer than any integral abutment that we've done in Vermont in the past. It's also on a skew, so this research that Susan was doing is very important to this bridge. But that being said, we always try to learn more about our structures and how they perform long-term, and specifically integral abutments over thermal cycles. So monitoring this bridge is going to give us an opportunity to be able to refine models that we do for future bridges, understand how the bridge will move and perform over different thermal cycles. And yeah, we're just excited to start collecting the data and see how this bridge performs in service. So.
Perfect, thank you so much. Susan, we'll go right down the list. First, what approach did you use to model the dense soil on the abutment wall? I have seen that displacement at the top versus bottom of abutment is sensitive to this.
Yes, let me just go to the, I think was it slide number 19 they were talking about?
The next question is on slide 19.
Oh, I see. Okay, so the thing is, I use nonlinear soil structure interaction, and I followed the plot from Enchirp for when, that's why it's in my slides. Let me, do you see my screen or should I share again?
If you could share again, please.
Okay. Let me share. All right.
Slide 4.
Okay. I think it would allow me to, oops, sorry. Here we go. You see what I did? This is the Enchirp plot that I converted to force displacement and plotted in, use it on nonlinear soil structure interaction into my model. Was that the question? Did I answer the question? Is that what the question was?
I think you got it, Susan.
Yeah.
Since you're already sharing your slides, the next one's on slide 19. Are the conclusions on slide 19 limited to straight, non-skewed bridges?
No, this particular bridge that I showed was non-skew, but let me tell you what I have been doing. I have tons of models on skew bridge. So what I have been doing, first I did my analytical work with a rigid plane with springs on the boundaries. Then I created skew bridges. I have skew bridges with 10 degree, 20, 30, and so on. And this particular model was non-skew. Here, the purpose was just showing EPS. As we know, because integral abutment bridges, you change single thing, everything changes, redistribution of forces. The focus here was geoblock. So this is non-skew. And you see here, I am showing the pattern of displacement profile of the deck, that what is happening. I was just trying to show that the most important thing is to model EPS as a block. If we go with linear springs, we never know what we are doing. Again, I have done that work also. I looked at the linear spring, and if somebody wants to go with linear spring, like for example, what I showed you, we are using Enchirp, then compare it to that. If your numbers are close to less than loose or something like that, you know that your model is too soft, is not representing your model. So again, I'm going to put those in my report that people have access to it. How do you make sure? To me, is the modeling is very big deal today because we have nice graphics, but we really don't know exactly what are we getting. So that's there. So this was 2D.
Perfect, thank you. Another quick one based on the slides. Is beta a friction force or a friction force coefficient?
It is friction force. So usually what we do, let me go to the page on that. I went very quickly. I didn't go into details very nicely because I have covered this before. We didn't have time. I knew that. Yeah. You see this beta that I'm talking about is just, according to ASHO, usually what we take percentage of the friction force is proportion to pressure, right? So it just, the material we are using, if it is soil, next to the abutment wall, that would be that friction. That's beta is a force. And when you add the wing wall to it, then that would impact the in-plane rotation. So beta represent that resistance parallel to the skew, the wall. And beta is a parameter, is not just the force itself. Percentage.
Great. And our next question fits along on this slide as well. Are the displacements in the beta/skew angle plots measured in the bridge longitudinal direction?
Yeah, this is the in-plane rotation, and it is in-plane rotation and in-plane, let me just, you see, for example, when it's this corner moves out, right? The deck rotates in plane rotation for the deck. By doing that, pushes joint, this corner, joint 3 moves out more than joint 2. If it was non-skew, nicely moves out and comes in. But this is just movement. And what you notice for long span bridges, that acute corners might go in. That's why you notice cracks at the corners. And the major thing here is length over width ratio has an impact. How much the bridge rotates? It depends. So that's why this analytic work is important with those plots. For at the beginning of any design, you can go look into it. What do I have? What is my L over length over width? What is my skew angle? Just go to the plot and figure these things out. Would be in the report.
Perfect. This one's not in the list, but are there any future efforts to create a design guide based on this research for use by national DOTs?
Actually, I really want help from others to help me to just I'm hopeful that it would be implemented by AASHTO. Because right now, when you look at AASHTO, it really does not exist the direct guideline. For example, when I was talking about skew angle, again, this particular of the project is just 1 hour lecture itself. That's why I just was jumping all over that. This, for example, to me, it has to be in the AASHTO, but I want input from everybody. If they like what they see, if they want to have a question about this, or still there is time, I would love to expand what I'm doing here, and I can work on those to make it something that be useful in a general form. And what I like about Vermont Bridge is, for example, it has all the things we have studied. It has a skew. It is a narrow bridge. It's a long span bridge. All right. So it's just like it has different stiffnesses at the abutments, soil condition, pile condition. So this way, with all the work that we have done for TIDC, now we are going to, based on instrumentation results that we get. Right now, we are in process of converting strain to stresses for Hartford Bridge, to checking things, that how things are, that then we start data analysis. Then I can create models and make a comparison that the existing, the real bridge behaves the way that I think it's going to do. So in other words, just want to make sure that streamline it, that everybody can use.
Great. Susan, I have 2 similar questions, both from one of our panelists, Jim. What do you mean by geofoam modeled as a block? And what is the difference between the 2 geofoams you talked about?
EPS 45 and 22. You see, if you look at the manufacturer, that's one of the complaints that I have about the manufacturers. Actually, we have to go dig all over the map to try to figure out the properties, because the companies making these blocks, and they have the properties of these blocks. When we say EPS 45 is the thickness, EPS 22 is it. Then it just like what's usually what like for the soil. For the soil, usually what I showed you what I do. Sometimes people use linear spring. I use non-linear spring and attach it to the wall. So in this case, what I did, I took the same way that I model rigid plane for other things, model my geofoam, and glued it to the wall, and then attached it to the wall and glued it to the soil. But I modeled it as a block element and a rigid element, not as a spring. So in other words, the same way, let's say, for example, a pile cap. When I say we have two ways of modeling the pile cap, I could have gone as a beam element, right? But that's too flexible. When you have like a solid cap, that solid cap has to go as a solid element. So did the same thing with the geofoam. And for Hartford Bridge, because we wanted to make sure that we see that is the geofoam moves with the wall. So those plates that Hart showed you, it just, we put it just next to the wall, then on the soil, at the end of the geo block to see, to look at the patterns. So the whole idea of the block is, I think, the best approach, unless, because you never know when you go with linear spring for geo block, what are you getting? Make sense? It's just like modeling terms I'm using for modeling different parts, because we have our girders linked to our slab, and then this as a block element.
Perfect, thank you. Did you have anything you wanted to add, Jim?
In particular, the geofoam, no. No, I think she.
Perfect.
Yeah.
Jim, you had mentioned that you were excited to work with this process on other bridges. Are there any in particular you're looking at in Vermont, or any particular plans for the future? Yeah, no, I think what I meant to say, or if I didn't say it clearly, is that I think using the results of this particular study is going to help us for modeling future bridges and improve our modeling. Maybe finding some areas where we have made some conservative assumptions based on actual data, and we can revise our modeling to address that. And also just seeing how this bridge performs, it's going to open up the opportunity for, you know, continuing to increase span lengths and look at different skew angles and allow us to put integral abutments on bridges where we would not have considered them in the past. And obviously integral abutments have worked out well in Vermont. We've been doing them for about 25 years now, and with a lot of success. They're a very durable structure. They perform well, and so our bridge manual tells us that it's our #1 choice for a bridge type, and so we want to expand the use of them, and this project's going to help us do that. Amazing. Are these limited to steel bridges only, or can it be opened up to concrete or alternative girders as well? Certainly not limited. I mean, you can, the thermal expansion in concrete's less than steel, so in theory you'd have less movement. So you could have longer spans probably with concrete than you actually could with steel girders. Vermont just has a lot of steel girders, and our longer spans tend to be steel girders. So but there's no limitation on the superstructure.
May I add to what Jim said?
Absolutely.
Yeah, I agree 100% what Jim was saying, that we go with it still because we want flexibility. I mean, they built it with concrete, but you see the steel is much better material to work with when it comes to this kind of bridges, which I agree with you. And again, this particular bridge has everything we need to check. And it just like, and we are going to just collect the data, analyze it, and see how it's behaving. And one of the things about, which is new with all the use of GPR, that if that is successful, it would be very helpful in future projects. All right, like that very easily, and it doesn't cost much to monitor the movement behind what happens to abutment wall for skew bridges. Skew bridges are, I mean, as Jim said, for larger skews, that would be very helpful.
Great, thank you, Susan. Moving on, Here's one. This is a little bit off topic, but I've been analyzing micropile supported IABS at shallow bedrock sites, and I was wondering about the requirements to reach depth of fixity. I found it not necessary as the bridge will contract/expand the same regardless of the foundation stiffness, but is still a requirement in the codes. Any thoughts about why that might be?
Let me see. The thing is, for when it comes to the piles, we go till we reach the bedrock, right? So this question is not clear to me because what happens is, actually, unfortunately, I didn't include it. I have too many slides that when you have a bridge, the distribution of forces is, there are couple of things. The pile and soil around it is one system, right? That each pile. Then you have walls, the wall and whatever is behind it, geoblock and that. So I don't understand that any changes you make on the pile, it would impact distribution of forces in the piles and the girders. It's just like it is, you saw what I showed you, that's just amazing. Take the soil, put the geoblock day and night. What happens to axial force? Unless I didn't understand the question clearly.
I would just say that in general, shallow bedrock is one of the reasons we don't consider integral abutments. So, and that's the fact that we don't reach fixity. I mean, in Vermont, we sort of have that requirement that we do. And I don't think it's dependent on the foundation type. I mean, I'm not a geotechnical engineer, so I won't speak out of my league, but I'm not sure how looking at micropiles versus steel piles would change that. But it certainly, I think I'd reach out to some geotechnical engineers with more experience.
Thank you both. The last question we have open in the Q&A, does VTrans have any plan to update the IAB manual?
Yes, we're currently updating, and it's in draft, our bridge manual, which will incorporate revisions to the integral abutment manual that we currently have. So the updates will be included in our actual bridge design manual that should be out this year.
Perfect. Thank you all so much. Do you, Susan, Jim, or Harsh have any last minute thoughts or words to leave our audience with this afternoon?
Actually, what I want to say is, please, anybody wants more information on these things or ideas, that questions, or I can study, look at it, and would be appreciated, contact me.
Perfect. All right. Well, if there are any further questions that we weren't able to address today, there's going to be a QR code at the end of our slides that you can put your question up, and we'll send out a reply, as Susan mentioned. And be on the lookout for more information for our annual conference this August 6th through 7th at the University of Maine. And lastly, the recording of this webinar will be available by this Friday, February 21st, with certificates of attendance being available right now. And I am putting a link to that in the chat. And an email will be sent to all registrants with the recording and the COA links once again when the recording becomes available. Thank you all very much and have a good afternoon.
Thank you very much.